Okay, now we'll go back and share the screen. So thank you for reminding me, Bree. Okay, so to find the center of a shape, it was really from integrating the x location center for each partial area times that individual section's area. That would equal the x overall of my total shape's center x point times its total area. To solve for that x bar, I can divide this by that total area. Because what we're thinking about integrating that is doing the sum of each x location times its segment's area, delta A, over my total area. Same idea for y, for its y center point. And if it's just a 2D shape or an area, all I need is that x bar and y bar. For a rectangle or square or center shape, I expected it's how to find the x and y center, like half the length or half the height. But for more complex shapes, this table is from your book. And so you can reference it. I don't expect that you memorize any of these. Again, you can use whatever notes you want on the test. Just no Googling, no talking to each other. So you can use your book, any of the slides I've had from class, anything like that. But for more complex shapes, I'm told the x and y bar here and their areas for shapes if I need to remember them. If I have a triangle with a base and a height, I'm told the y bar based on that height is that height divided by 3. I'm not told an x here because a triangle, you could arbitrarily define what is the base and the height. But base, in which case I can use the same equation, except now you're set for the value, it's finding the x bar value. So do keep that in mind. Some of them require a little bit of thought to think about how to use them. So I have shapes here, center points for triangles, quarter circles, half circles, areas under a parabolic curve, a part of a circle, and then also with curves and lines, a quarter of an arc, a half an arc, or just some segment of a circle. Okay, so we're going to use our properties of knowing how to find a centroid now to solve this problem here. I have a homogeneous wire, A, B, C, D, and it's bent, obviously B here as shown, and it's attached to a hinge at C. I want to determine the length L, this distance from C to D, for which the portion of BCD wire is horizontal. So if I think about a hinge, it could support a Y force, right? So it can make a force in its Y direction as a reaction, but X, Y is about that hinge. So I can't have a force on my X change, which really just means my X center point needs to be at C if this is horizontal. Otherwise, if it's not, it's going to tilt, right? If I have more weight on this side than the other, or I have more weight on this side, it's going to tilt that way because that hinge would allow rotation. So I really want my X center point to be along this line C and A here. Why am I? Pen is not wanting to work. There we go. So, oh, go away. So my to be here, and to this for this to be my x-axis. Since x and y-axes aren't labeled here, I get to choose where I put them. But if I make my y-axis here and therefore this is x0, that means that I want my center x value for this whole line segment to be at x equals 0. And as we'll see, that'll make the equation a little easier to solve than if you wanted your center to be at like an x value of 5 or some random value. So, okay, so how am I going to do this? And my general rule is that I would dA over my A would get me x bar. When I'm talking about that for a line, I'm not talking about area. I'm just talking about length. A line is a kind of like one-dimensional instead of two-dimensionals with area. So in this case, I can say x bar equals the sum of each x coordinate for each line segment, dl for the length of over L. Length delta L. total length of my line. Same thing with y bar, it's have to be y dl over that. So I'm going to make myself a nice table here based on line segments of this whole A, B, C, D thing. So I'm going to make one segment AB, and make another segment that's from B to C, and another segment from C to D. I'm going to put in a nice table. For each of those segments, I want to know, well, we'll start with the other thing. I want to know what its length is. So that's going to be my delta L. I want to know what its X center point is, what its Y center point is. And then if I multiply X dl, that can get me the sum of these, as we'll see. So for AB, that's from A to B here. What is my delta L? Or how do I find that delta L length? Okay, so Binmit got it's 100. How'd you get that? It is correct. That is correct. Binmit, how'd you get that?
Pythagorean?
You typed it 100 was our length segment of AB, right?
Yeah, I squared both of them. I added them and put them in a square root.
Okay, so you're taking the square root of what squared? Here.
60 squared plus 80 squared.
Wonderful. So I basically said this was a triangle, and I used Pythagorean theorem that I'm looking for the hypotenuse, right? Would be AB. This would be my X and this would be my Y. Didn't get that. And that got me 100. What is DL for BC? What is the length of line segment BC, just from B to C? Anybody? Good. 80. That's labeled for me. What is CD? From C to D, what is the length of that segment? L. Good. So I don't know what it is. It's my variable, but I need to write it in terms of that variable L. What about the X center part based on how I've defined my X-axis here and Y-axis? So positive X would be to the right, negative X to the left. What will be the X center of line segment AB? That one's a little harder to think about. Good, negative 40. How do we got that? Its total X distance was 80. Since it's a line, it's always going to be half that distance. And it's negative because it's going to the left of that. So negative 40. BC also happens to be negative 40, hence I started writing there. What am I going to call the X coordinate for my center of line segment CD? Good, L over 2, we're getting this. Now, technically, I only have to find the X coordinate because, again, that hinge could support a Y force that will counteract any Y weight. My Y center will not be at that hinge, right? It's going to be somewhat below because I do have some weight down here and nothing above to cancel that out. But it's really the X only matter, but it's a good exercise. Let's play with the Y if I needed to know the Y center as well. What would be my Y center of line segment AB? Y center of BC? 0 based on how I find it here. So that, and similarly, CD is also 0. Okay, so now to do this equation, I need to multiply X times DL. Right? If it was an area, I'd be taking that X center point times DA. Since it's a line, it's one dimension, just as length. I'm going to take X, negative 40, and multiply it by 100. It's 140 here. I have 80, 40 here. And what will I get for CD when I multiply X times DL? Good, I get L times L, which is L squared over 2. Okay. Put in this equation to get my total X center point. I need to sum up all of my X DLs. So take the sum of this whole column. And I also need to sum up to get my total length, all of my line segments. Okay. X bar by taking the sum of those over the sum of this. Want you to try to solve that what am I going to set x bar equal to based on how I've made this diagram here to mean that this won't rotate about this hinge? What do I need my x coordinate center point for the whole line to be? I needed to be at point C, which what x value did I make at point C? Yeah, that's 0 based on how I again made this coordinate system. It's not for me, I can define it. So you want to set it your x bar equation equal to 0, and that's from doing the sum of your x dl over basically the sum of your delta L's gets you your total L, right? Solve that for L, and that's your one of your Echo 360 questions for today. So you can talk to your chat buddy about it if you want. I'll leave this open here, and then I'll go to the Echo 360 in a minute once everyone has those written down, hopefully. I'm solving that then for what does L equal when I set that equal to 0. Okay. See if I can. Oops. So hopefully you can see enough of that. It looks like Echo 360 is working. It was not working in my earlier today, so I don't know what it did. Having issues with it recently. I'll give you about 30 more seconds and look at results. You can keep on submitting later, but we'll go through this about 30 seconds. Okay. Good, so most people do get correct. It should be 120 millimeters. If you didn't get that, how do we do that? So my sum of XDLs, I had 100 times negative 40 plus 80 times negative 40. That got me to 100 plus L squared, that's 180 plus L, and I end up dividing that and setting it equal to 0. Why 0? Again, because that's how I define my x point at C. If you had made your x-axis, like your y-axis start here, which meant this was x is 0, then you would need to be setting that equal to 80. In my opinion, just makes that a little harder to solve for, but mathematically would be the same idea. I want that to equal 0, which means if I multiply this whole denominator on that side, that's still going to equal 0. Means just my numerator really needs to equal 0. So when that's 0, I move negative 7,200 to the other side. All that 7,200 equals L squared over 2. Well, 7,200 times 2 gets me 14,400 equals L squared. Take the square root of that, and I get L equals 720. My whole units this whole time have been millimeters. Okay, questions or concerns about any of that problem? Finding the center basic line. And if I needed to know the y center, I could have done y times dl as well, summed it up, divided by its total length. I just didn't need to know the y value here because that hinge can support that. Oh yeah, 120 to look like a 7. What I wrote, thank you. 120 millimeters. Okay, let's do one with an actual area, not a length of a line. I want to calculate the centroid of this area shown in blue. So to do that, I'm going to divide it into segments that I can easily calculate the area for, which is going to be divided into rectangles. You could actually do this one of two ways, but I'm going to decide to make your rectangles. This one at the bottom I'm going to call 1, and it's going to go all the way to the end. And therefore, the area on the top I'm going to call 2. I like actually drawing them out, because otherwise you might confuse with this overlapped area of which like part of your area you're going to use that area for. Are you going to use it for 2 or 1? If I draw them out, then it's easier to see my delineations between them. So same idea. Now I would need each delta area for each part, 1 and 2. The x coordinate, need the y coordinate because I want the whole center point. That means an x and y value. And then I'm going to sum those and divide by their total areas. So what is my area, or dA, little area, for part 1 here? Or how do I find it? Length times width, good. So my length is 240 millimeters, my width is 30 millimeters. I multiply those together, and good. Michael, I got 7,200. What about area for 2? How am I going to find its area, or what is it? Okay, so I see you kind of divide between 8,100 and 9,000 in the answers. Which one is it? Well, that's again why I have to be very careful with how I draw these. If I took area 1 all the way to the end here, then area 2 doesn't go all the way down. It starts 30 millimeters up. So I have to take 300 minus 30 millimeters is this length. Then multiply it by 30, and that gets me 8,100. Or you could take the total area and subtract that. If you draw your lines sometimes, then you forget which area you used and what part, and you'll overcount that area. That won't get you the correct answer, okay? So do be careful with that. What is the x coordinate center for part 1? If I actually have my x-axis defined here for me, so I've got to use its values. Here's x, and here's where y starts. Yeah, so it's half that length. Half of 240 is 120. Your next Echo 360 question is, how do you find the x center? What is it? For part 2. So I'm looking for the x center of part 2 here. Okay, 30 more seconds. Confer with your chat buddy if you'd like. And what do we get? You can still be submitting, but I'm going to show. Oh yeah, most people do get it's 225. Why is that? Because again, where I define my coordinate system matters. So if x starts over here at 0, I've got to go all the way to then half of this x distance. Total distance was 240. Half of 30 would be 15, so I got to go 15 back, or 240 minus 15 to get to right there. And that gets me 225. Questions or concerns about that? Okay, what about y bar? for part 1. Good, 15. That's my y value. Y bar for part 2. See 2 different answers right now, 180, 150. 135 is another possible option. And 65. Getting a lot of different answers. So how do we get y bar here for part 2? Well, I started part 2 at the top of this, so that was 30 up from where y was 0, right, at that x-axis. And then I need half of my total y distance there, which was 330, 300 minus 5. My 270, divided by 2. This guy was 300 minus 30, 70. Of 270 to get half its height. Questions or concerns on that if you didn't get it, because we had a variety of different answers at the beginning for that. You can be very careful where your x and y axis are. Okay, now how do I take x dA? I multiply x by its area. Got a kind of waiting for that. This is like wait. I get 864,000 for x, and I get 225 times 8,100, 1,800,225. How many numbers do I have there? Way too many. Something like that. Y dA, take y times its dA, 15 times. Oh, nope, 8,000. Y times part 2, 1 million. My commas correctly. This might be when I'm like, oh, these are such large numbers. If you had converted this to meters instead, that would make you not have such large numbers. So that's an option. Just keep in mind at the end, you probably want to transfer back to millimeters since that's what you were given initially. Otherwise, there's nothing really scarier of large numbers as long as you're using a calculator, but keep that in mind. So now what do I want to do? Now that I know x dA and I know y dA, what do I want to do to try to get x bar, my total x center for this part? Yeah, I take x dA and the sum of together and the sum of this column, sum of my areas. So see if you can do that. Take that Echo 360 question, but you can type in the chat your answer for those. Okay, and looks like a lot of people are getting that. So my X should come out to be 175.6 millimeters. Okay. So moving on from doing centroids, the video lectures for this week, we got into then chapter 6, where we're looking at trusses or frames. And we said a truss is a structure where we have members that are connected only at endpoints, and they have no forces in anywhere that isn't an endpoint. So like A and C is one member, and it only has forces at its end of A and its end of C. Similar, C and D is one, etc. from that. They tend to make kind of other structures where you can add beams to that, and they're very nice for rigid structures because they can support forces in moments without collapsing. So hence building tall buildings and bridges and stuff do well in that structure format. How I can analyze these trusses, one method is called the method of joints. And to do the method of joints, I didn't actually write it in here, but it's in key first part. Your first step is to actually analyze the whole structure together. So these are all analyzed like they're 2D structures that have thin thickness beams. So at equilibrium, I get for 2Ds, remember sum of forces in X and sum of in 0, and my sum of my moments at some point equals 0. I want to do this for my whole structure first, like for this, and then I dismember or break each part of that truss into its individual members and create a free body diagram for each joint. Okay, so I write like the reaction at A, then had X and Y components. It likes to draw this as a composite arrow for that reaction, X and Y. I like just leaving them as the separate horizontal and vertical components, X and Y of A. But then how this member AC acts on it could either be pushing on it or it could be pulling on it. Always draw my joints that each member is going to be pulling away, like we have been doing with cables. Remember, we assumed cables always had to be support and compression, which meant they were always pulling away from their point of connection for a structure. So I always draw a beam pulling away. That would be from A to C in this case. And then I would draw this beam from A to D, this member, pulling away from point A as well. And then this was my, that does not write, AX, and this was my AY reaction force. Similarly, I look at my joint at D, pull apart all of its members, and how it would have reactions, pulling up, white D, pulling to the left, to the right, and down based on P, which is an external force applied. And then at B, same thing, a reaction force. I will have a force pulling away or pushing that member CD, CB, and for this member DB. I'm always going to draw my arrows as if they're pulling away, again, like we've been doing with cables, because that will be in tension. So my default is going to be that my member's in tension. If I end up calculating values for like the force in CB or the force in DB here in these members, and I get a negative value, then all that meant is that it was actually in compression instead. So if it calculates negative, compression, not in tension. If you do the reverse, like they did with member BC here, they drew a reaction force acting on that joint B, then it meant you were assuming this was in compression. See, that meant that your member here had to have an equal and opposite reaction on the member. So if it was pushing on B, it means it was also pushing in on that member. and that would be in compression. I like to assume the default of tension because I'm used to it with cables, and then work from there. You then get equations at each joint. Technically, you're doing your same equilibrium equations, but analyzed at each joint like a separate body. It's just when you're only at a single joint, your moment equation doesn't matter because all of your forces are going in the same point. So you're really just summing up forces of X and Y, as we'll see. There's also the method of sections that can be used to analyze trusses or frames, where you basically draw a line cutting your frame apart. It doesn't have to be cutting the frame equally in half, or the truss structure. It could be cutting this way, circle through, right? I can't just say I'm going to cut up here or something like that. But it can go through in any shape. It could be a squiggle shape, whatever. It doesn't have to be a straight line. That means you can then kind of divide your truss or structure into the side that was on one side of that cut versus the other side of that cut, and treat each like its individual free body diagram. So now anything from the cut, any members you actually cut, like I cut member BD here, I get to see the force from that member as an external force applied to this joint B. Similarly, BE was cut, so I see it as an external force applied to point B. Again, both of these would be assuming in tension because they're pulling away from that joint. At C, also I cut CE, so I have to draw it externally. Anything in here I didn't have to draw AB or BA because now it's internal and I'd have it force going one way here and the opposite way there. So each forces will have equal and opposite reactions, we know from Newton's law. Method of sections is probably a little bit easier if you're only solving for like the force in one member or for a few of them, particularly if they're members close to each other. But if you needed to solve for the forces in every member in a structure, it's probably going to take you longer because I can't solve here, right, for the force in member AB because I didn't cut it, so I don't see it. It's like an internal force, it's not external to the structure. So I'd have to make another section through there to analyze it. If you want to find the forces in every member, method of joints works better. But method of joints would take you longer if you only needed to solve for one or two forces, not all the members in total, in which case method of sections would be better. So keep that in mind, depends on what you're asked. So let's do this problem here. Using the method of joints, because it blatantly told me, determine the force, and each member of the truss shown. Now, if it even hadn't told me use method of joints, since I'm the force in each member, then joints is probably easier because I got to solve for each one anyway. I don't want to make a whole bunch of separate free body diagrams to make different sections. So that's how I decide that if I'm not told. And then I need to state whether each member is in tension or in compression, right? So how I solve that first is I do equilibrium for the whole body without dismembering them first. That means I need to look at any external forces. I have this 480 pounds pulling down at D. I have what type of reaction here, or what type of support at A? Anyone remember what this little symbol's reaction was? Does it mean I have a reaction or connection at A? Or what kind of reaction force would it make? X, Y reaction forces or moments about that point? What can this thing do here? Yeah, so it's a pen and it can do an X and Y. It can't make a moment. X and Y forces. So I'm going to write externally that this is AX and that this is AY. Again, I'm always in my x-axis positive to the right and y positive up, so I like that. What about at D? It's a little hard to see here, but they're little circles, or you could think of them like wheels at the bottom of this reaction. What type of reaction is it? And therefore, what sort of forces do I need to draw at D? So we did that in last week's lectures in class. Yeah, so it's not just Y, it makes a force perpendicular to this surface, which in this case, this surface is going Y, perpendicular to that is X. So here it makes this dx, because it's basically keeping the structure from pushing through the surface here. But because it can roll, it can't counteract any forces in the y direction because I have little wheels that would roll about y. It is a roller. So keep that in mind. You don't have to memorize those, but you do need to go back and reference them. Otherwise, you don't put the correct external forces on your diagram. So based on this, the whole body, I get some point. So what I have defined arbitrarily positive as in to the right, dx that they have to sum up equations. What are my y forces that are going to equal 0? Minus 480 because that force is going down, negative. And I like to take my moment. Where would I like to take a moment? Well, I really would be the same whether I take it at D or A here. They both have two forces acting. Let's say I take it at D, in which case dx and this force don't matter because they're both acting on point D. They have no distance separated from it. AX, how would I write the moment due to force AX? Well, it's a distance perpendicular to D of 9 plus times that force AX. Is it going to be a positive or negative moment? Well, I put my fingers from D going to A, like this would be R, and then I curl towards A. Okay. What moment would AY make at D? Anybody? Or how would I write that moment? Good, CJ, no moment. Why? Because it has no perpendicular distance. Remember, you can move a force equivalently anywhere along its line of action. That line of action moves into D. You're looking for the distance 2D moment. You're like, there is no distance. I'm really so D here. So now I can go back to here. What does D have to equal? So 0. Okay. AY minus 480 has 0, AY equals 480. Okay, that got me all my external forces. Yay. Now I get to look internally by doing joints. So I'm going to look at joint A. What did I have? I had, or you could not draw it because it's 0, but out of convention, I'm going to still draw it here just so we see it. I had AY from the reaction forces there. And then I'm going to have a force. Again, I always like to default draw them pulling away, which would be in tension. AB and AC. So at A, now I get to do equilibrium again, which is sum of forces in X and Y. Technically, it'd be a moment equation too, but when you're only looking at forces at A, all of them are going to make a 0 moment, so it's not a useful equation. But for X, I had AX, although that's going to be 0, plus AB, plus AC, I need the X component of it. What would that X component be? I can make myself a triangle and try to find that angle theta. Would be here from horizontal. You could either make yourself as that triangle going the whole distance, or that means my y distance is 9 plus 9. 18 over my x is 7.5. So inverse tangent of 18 over 7.5. Opposite over adjacent is tangent, inverse to get that angle. Or it would be the same thing as inverse tangent. You made your triangle a little smaller, stopping at C. That meant you y distance was only 9. Your x distance had to be half of 7.5, since you moved half your height to by similar triangles. So that would be 3.75. So do be careful which y you're matching with what x distance. So I get that angle equals what? and do inverse tangent of either one of those, I get 67.38 degrees. So how do I write the x component of AC now that I know that angle? I write AC cosine of 67.38. And the nice thing about this frame structure is I'm going to see that same angle in a lot of these. So once I have that angle, I can use it. Some of my y forces, I had AY, and then AC's y component would be going down. So it would be negative AC. The y component is from sine or adjacent, opposite over hypotenuse of that same angle, 67.38. Okay, so I could do that, and I could solve then for what I already knew AX, I already knew AY. My only two variables are AB and AC. You can do that exercise at home if you want, but I'll go ahead and tell you what they are. So AC comes out to be 520 pounds. AB comes out to be negative 200 pounds. What does that mean? It's in compression. Good. I said my default was I'm assuming tension. This meant this guy was in tension because he lost it. I do the same thing moving to B. So what reactions do I have at B? Now I'm going to assume I'm pulling away from B. The same thing that I was at AB though, right? It had to be the same force pulling this way as it was that way. So that was still AB. I already know what that is. That's nice. Now I have BC and I have BE. BC would be following the same kind of angle rules here. Just got to be careful that this angle be the same as that angle. I can sum of its forces in X and some of its forces in Y, and that would get me my two variables BC and BE. I already knew AB. Can do the same thing at C. Do it for every joint. So at C though, because you're going to have forces going equal and opposite directions, one of our rules of trusses that can save you a little bit of time is if it's the same angle or goes along the same line, but opposite directions, like the C, and this component would be CE, they have to be equal to each other if there's also equal lines going this way, or if these lines don't exist at all. If there's only one line, then they won't be. But AC is going to be CE equal to CE here, and this was BC, and this was CD. BC would also have to equal CD. If you don't like that simplification rule, you can still always do sum of forces in X and Y. It just, the shortcut saves you a little bit of time. And it only applies when either you only have two forces and they're opposite but along the same line, or like you have four here, so each one is its own pair of lines. If you have three or some odd, then that's not always necessarily true. They're a weird angle, so keep that in mind. At D, do my same things. I will have dx going in. I have my external force, 480, pulling down. Then this was CD, and this was DE. Okay, and so from C, because I already knew AC, I can know CE. And because I already knew BC, once I solve for B, I can get CD. So BC here, actually, if you want to know the answer I got for that one, save us some time, is 519.48. And BE came out to be negative, which again meant compression, 479.5. So they're then the same as CD and CE. I know them here. And I already knew DX and 480, so actually I'd just be checking that my values work there. My last joint would be at E. I have forces E, or that we, I'm going to call it the same way, just pulling away. Always CE here and E here. Since I had already found DE from this, I can use it at E. So at each joint, it should then solve some more of the variables that you can then use in the next joint's equation and move on from there. So that's our method of joints. It's just a little bit extra math. I'll go ahead and write out all the final answers if you want to check doing this at home with algebra for you. So we got BE. We then got that C had to equal BE. So CD was also 519.48. And CE had to equal BC. So did I write that one correctly? That one was also 519.48. Get it that right. CD. Double checking, sorry. Where did I have CD? SEC. Okay, yeah, both of them. Equaled is my last one to solve for. Yep, know all the rest of them. AC equals CE. Yes, why did I write that wrong? AC is 520. AC has to equal CE. I wrote that as C when it's CD. But both of them weren't that. Okay, so that's joints. Again, sections would have worked similarly except for external forces applied wherever you make the section from that. Because I wanted to solve for all the members here, it was easier to do joints than sections. Questions or concerns over any of those? Oh, for some reason I thought class ended at 3:20. That's why I was trying to rush through that. We had 4 more minutes, so I can go back through more.
This was just like a little bit ago, and I don't know, I still get confused about it, but like when you were taking the moment at
Yeah.
D, like how did you know what direction? I still get confused about the right hand rule, like I'm not even gonna lie.
Okay, so
Like
for
what
right hand
direction
rule,
going?
how I like to do it is I put my wrist at the point I'm taking the moment. So I'm making my wrist D in this case. It's going to take my, okay? We okay with that? So I'm calling my wrist D. Your 4 fingers then need to go from the point you're taking the moment, in my case D, to where your force is acting. So in my case, I'm having to go from D up. My force was acting at A, and that was what we called R traditionally, because you're really taking like R cross F. That's how we'd written that.
Mm-hmm.
So your 4 fingers are R, and they're pointing towards where that force is acting. Again, they started with your wrist being the point you're taking the moment at. And then you want to curl those fingers in the direction of your force. So my AX force was going to the right because that's how I had arbitrarily defined it. I want them to be positive X, so I didn't have to write negative. So that means I need my 4 fingers to the right. While they're pointing up, still looking like R, they need to move to the right. The only way I can get that to work is my thumb to go into the screen. Right? I can't bend my fingers backward. So into the screen is a negative moment. Thumb pointing out at you is a positive moment.
So we're talking about the AX force.
Yeah, so AX was going to the right is how I had arbitrarily defined it.
Okay.
Needed to be able to curl to the right, not to the left. If I defined it to the left, then I'd make that a positive moment.
Okay, sweet.
In this case, it didn't happen to matter because it ended up equaling 0. But most of the time, that sign
Yeah.
really does matter, right? So you do need to know how to do that. Does that make
Yeah,
sense?
thank you.
Other questions or concerns? I can go back more through right-hand rule or equations. Are we doing that?
Can we briefly go back over 5.1, like how we were calculating like the dA, the x, and like the y and stuff? I kind of got lost.
Yeah. So I'm always going to divide my area, assuming the area is not just like a single shape. Right? It's not a single rectangle. It's not a single circle. It's not a single triangle. If it's a single shape, then you just get to find like the x of the center, which for a rectangle is half its x distance, and for y would be half its x distance. Or if it was a single other weird shape, I get to use my table, like a triangle. And again, I don't expect you to memorize any of them, but I expect you to use them and reference them. But my shape here wasn't a single shape. It was really composed of 2 rectangles. Does that make sense?
Yes.
Okay. Now, there are 2 different ways you could define these rectangles. I defined my first rectangle as going the entire length, right? So it went the entire 240 millimeters in X and then up 30. You could have cut it off at the end and made it not go the whole length, in which case it would be 240 minus 30 for its X distance, but I left mine the whole length. Draw their boundaries, because otherwise when you get complex shaped parts, if you don't draw where you're counting boundaries, it's really easy to count an area twice. Does that make sense?
Yes.
Okay, so area 1 I got by doing the 720 number was from doing 240 millimeters times 30 millimeters, right? It's length times its height in this case. That gets me 7,200. Area 2, its length or width here is 30 millimeters, but what's its height? I need it to not overlap with area 1, right? Otherwise, I'm counting this kind of square at the bottom here twice. So I had this whole length was 300 millimeters. I had to subtract 30 because I used 30 bit of that height to do part 1's area. Does that make sense? So area 2 ended up being 30 millimeters times not 300, because that would be that total length, but 300 minus 30, or what was 270. Does that make sense?
Yes, that does. I think earlier I wrote down 270 twice instead of 240 for the first one, and I was confused, but that makes sense.
Okay, so that's how I got 8,100. Okay, those are my individual areas of each section. Now I got to go find the X center for each section and then the Y center. So the X center for 1 is just half its X distance. 240 divided by 2 is 120. For section 2, again, I really needed to be looking at my X and Y centers based on where you made your X and Y axes. If they are given to you, you have to use their axis system, or at least convert back to that at the end. If you're making your own, you could define it how you want, like I kind of did for this line one. I defined that I was making my y-axis start it right at C.
Mm-hmm.
But here it's defined for me, so I'm going to use their system. X started at a 0 of here, right? Because that's where my y-axis is. So I got to move all the way over to here and then find what its X center, which would go through this line, right? But where is that point?
Okay.
That is the total length of 240 minus half of this width, right? Because I'd be okay if I just drew that rectangle and I said it's half that width. But if you don't keep up with the coordinate axis, then you don't keep up with, okay, I'm weighting this side way more than the other. And I should double check when I finally get an answer that it made sense, that like my X isn't just half of 240, it's a little weighted more on this side because I get more weight here, right, than I did on this side. And my Y should be weighted a little higher, a little lower than halfway, because I get more weight down here than I did above.
Okay.
Does that make sense? For X was then 15 for that one, but for this one, it became 165. How did I get that? I did 30, because I had to go 30 up for my part 1, plus half of this Y distance. That total Y distance we said was 270, 300 minus 30. So it's a half of 270, that's 165.
Okay, that makes perfect sense. I like wasn't even paying attention to like the axes, and I like got confused because I was writing everything down. That
And-
makes sense.
Again, they could not be defined as axes for you, but in which case you need to define them and stick with them. Because you can't just move your axes for how you define part 1 to part 2 if they need to combine together, right? I need to know, was this one further over to the right or left than the other one?
Okay, that makes perfect sense. Thank you very much.
Sure.